I'd like to welcome everybody to the webinar. This evening we'll be talking about lacrosse shot biomechanics and the biomechanics of producing speed and power with respect to the shot. Again, in looking at this, we're going to be talking not so much about the physical attributes, the strength components, the anatomical components, or the superficial mechanics of the shot. We'll be talking specifically about the biomechanics. And the biomechanics really relates to or refers to the athlete's ability to coordinate their physical attributes, their strength, range of motion, stability, anatomical, structural components into the shape of the actual shot. So we're going to be looking below the surface of what you see as the technique of the shot, and looking at how the athlete coordinates the effort of producing speed. And that's really what we refer to when we refer to the biomechanics. So when we refer to shot speed and power, the key to this, shot speed and power are achieved through the ability to essentially crack the whip. Cracking the whip refers to something we call the kinetic link, and that is the ability to create momentum with large, heavy body segments, and then essentially conserve that momentum or pass that momentum along to smaller body segments, ultimately all the way out to the most distal end of the system, in this case, the lacrosse stick and ball, accelerating the ball out of the net. And in conserving momentum through the system, creating, in a very efficient manner, creating maximum speed output. So essentially, shot speed and power, as in any distal end acceleration, any throwing or swinging pattern, is really achieved through the ability to essentially crack the whip. Now, cracking the whip is essentially a product of three key biomechanical areas: lower body mechanics and the ability to use ground reaction force to produce torque; core differentiation, the ability to essentially turn torque into speed; and then bracing, or what we'll call snapping the stick or snapping the whip, the ability to then take that speed that's generated through the core and accelerate the implement to its maximum speed most efficiently. So the three key areas that we'll look at with respect to cracking the whip or producing shot speed in lacrosse will be lower body mechanics, core differentiation, and bracing. Now, if this is the first time that you've joined a webinar, if your specialty is lacrosse and you haven't participated in any of the other webinars you've done in baseball or golf or any of the other sports, this stuff is relatively new. For those of you who are maybe strength conditioning specialists, partners of ours, or athletes, multi-sport athletes that might be joining the webinar, you've heard these three components a lot. And really, although each sport has its own intricacies and its own sort of flavor, any time the body is trying to accelerate a distal end, whether you're throwing something or swinging something, the body uses the same basic principles or the same basic biomechanical parameters to create distal end speed. And they basically boil down to lower body mechanics, core differentiation, and bracing. So these are the same components we talk about over and over again. However, we obviously place them in the context of the specific athletic endeavor, in this case, the lacrosse shot. So we'll start by discussing and talking a little bit about lower body mechanics first. Lower body mechanics boils down to two key parameters for us. The first is lead knee extension and the ability to essentially lead leg stabilize. So what I have here is a little diagram of a lacrosse player highlighting the lead leg, whether you're shooting lefty or righty, whether you're running into the shot or standing somewhat stationary, doesn't matter. The same basic principles are going to apply. The lead leg in particular and the ability to stabilize the lead side is absolutely crucial in creating torque. So what essentially happens, although the backside does produce some, or does participate some in this production of force, the lead leg is paramount. And what happens is the lead leg presses into the ground to create friction, or uses normal force to create friction, and then presses along the surface of the ground to create shear force. When it presses along the surface of the ground to create shear force, the ground will press back with equal and opposite force. The athlete then has to translate that ground reaction force through the ankle, through the knee, to the pelvis to create a force at the pelvic girdle. That's what creates rotational speed, or what we'll refer to as torque at the pelvis. So lead leg stabilization is absolutely crucial. What you'll see in elite level athletes, elite level lacrosse players with high speed shots, is that they come into contact with the ground typically with their knee bent at roughly about a 45-degree angle. That knee stays in that roughly 40 to 45-degree angle for almost the entire acceleration phase of the lacrosse shot, which is a very compressed period of time. Lacrosse shot, of all the sports that we look at and we measure and assess many, many different sports, lacrosse is probably the most ballistic activity that we look at. It happens in the shortest amount of time with the highest speeds. So what we're looking at in this graph is foot contact, or the application of force into the ground, and with this first vertical line, and the second line is the shot of the release of the ball out of the net or away from the stick. So what we're looking at is a very condensed period of time. This is right here. This whole graph here is about half a second. So you can break this down and see we're talking about literally fractions of a second. But what's imperative is that the leg come into contact with the ground, or the knee, I should say, come into contact, or the knee position, let's say, should be at about 40 to 45-degree angle as the foot comes into contact with the ground. It then needs to stabilize in that position so that the force that's applied here and the ground reaction to it can be translated to the hip and to the pelvic girdle, which allows for the creation of torque and essentially the initiation of speed development. And we'll talk a little bit about where athletes break down here in a little bit, but lead leg stabilization is absolutely crucial to creating speed. So you can have a kid that's strong, that's flexible, has mobility, that has all the attributes, but can't stabilize the lead leg, and he's just going to be struggling. And they may generate some speed, but their true potential is not going to be really seen, and they're going to struggle. And then compensations always breed injury, or at least the higher potential for injury. So lead leg stabilization, the ability, the strength and the capacity to do it, as well as the neuromechanical coordination to do it, are absolutely paramount. And because essentially we start at the bottom, we start at our foundation and work up. So it's our interaction with the ground that drives the rest of the process out to the stick. If something breaks down here, then the rest of the movement, in most cases, is going to be compensation. So I can't stress enough that lead leg stabilization is absolutely crucial to creating shot speed. And when I mean shot speed, I'm not just talking about distal end speed in terms of the speed at which the ball is being released out of the net away from the stick, but also the time frame and the ability to be explosive and quick about accelerating the shot. Getting the shot off is not just about how fast you can fire the ball, but how quickly and how explosively you can pull the trigger. And lead leg stabilization is absolutely critical to both of those. The next thing we'll look at with respect to lower body mechanics is what is occurring with relationship to the lead leg stabilization and interaction with especially the lead foot. One of the key components to being able to produce shear force and that we want a high level of ground reaction force to produce the maximum amount of pelvic rotational speed possible. And what's happening is the athlete, whether they're standing still and they just bump forward or they're running in at full speed, they are manipulating their center of mass from a linear perspective and turning that linear motion into rotational speed. So one of the things you'll find at high-level lacrosse is that their ability to control their center of mass is absolutely critical, and their ability to decelerate their center of mass quickly relates to speed output and explosiveness or quickness. So what we're looking at in this graph is from the point of foot contact to just right at release, there's a massive deceleration in forward movement of the center of mass. So they're able to, it's body awareness or proprioceptive awareness. The athletes aren't aware that they're doing it, but they're using their body weight and their momentum to create the sort of the linear component facilitates the rotational speed. So their ability to control their center of mass, decelerate their center of mass quickly, and turn this forward momentum and the deceleration of forward momentum into rotational speed is also absolutely critical. However, their control of the center of mass and their ability to produce this rapid deceleration, which facilitates the acceleration, is very much dependent on lead leg stabilization. If you can't lead leg stabilize, you're not going to be able to control your center of mass. So again, as you move up the chain, each parameter is going to be reliant on the previous parameter. So you can see how important lead leg stabilization is to the mix. Next, we'll talk about core differentiation, your ability to translate that torque or that ground reaction force and pelvic rotational movement into distal end speed. So what we look at here is as the lower body accelerates as a function of the ground reaction force, the lead leg stabilization, and the control of center of mass, or the rapid deceleration of the center of mass, there is engagement of the core musculature and transfer of speed. That's the cracking of the whip. Transfer of speed from pelvis to upper thoracic. Graphically, if you look at the same basic movement, you see foot contact, release of the ball. You'll see that as the foot comes into contact with the ground, the pelvis is accelerated to its peak output speed. The muscles are engaged. The pelvis is decelerated as an anchor to accelerate the upper torso to more than double the speed. So you get this incredible burst of speed through the core. We call it core differentiation because the upper thoracic or the upper torso here has to move somewhat independently of the lower body or the pelvis and has to be facilitated by the engagement, both the lengthening and the shortening of the core musculature. And a lot of athletes, especially young athletes, don't develop that sequencing and that coordination pattern. And as a result, they're not able to create or more than double speed as they move up the chain. And they lose, so for whatever they might create at the lower body in terms of ground reaction force, they lose the ability to transfer that speed out to the stick because they don't differentiate or coordinate through the core. So they have to stabilize the spine and stabilize the torso at the same time, move the pelvis versus the upper thoracic torso in a sequenced way to get this exponential development of speed. And so it's absolutely key. So you can do great things with your lower body, but if you don't have core coordination, core differentiation, you won't be able to do much with what you produced with your legs and the ground. So core differentiation becomes absolutely critical as well. And it's another area that lower level athletes struggle with, higher level athletes have developed. So when you're working with your higher level athletes, you want to hone this, you want to perfect this, you want to improve it. When you're working with your lower level athletes, you want to just develop the pattern. Most of your younger kids don't dissociate body segments very well or differentiate body segments very well. So we want to just teach the nervous system how to differentiate, how to proprioceptively be aware of the differentiation as well. And these are things that are absolutely critical to performance that can either be enhanced or developed depending on what level the athlete is and in a lot of cases what developmental stage they're in, what age they're in. The last thing we'll take a look at before we go a little bit deeper into really the key parameters and how significant they are, is this idea of bracing or cracking the whip. Bracing or super stiffening is a concept that's been talked about in many different ways. There's many researchers, including individuals like Stu McGill, that have talked about, who have seen the dynamics of what they call super stiffening or bracing, and have talked about it. We measure it using motion, 3D motion capture, when we can actually measure the ability to brace and accelerate. What it really refers to is a rapid, an extremely rapid deceleration or stiffening of base segments to accelerate the extremities. So the ability to brace at the core allows you to accelerate your extremity with maximum efficiency and maximum output. Let's take a look at the way this looks in lacrosse shot. What you're looking at is you're accelerating your arms. If you think of the arms as a unit here from the top of the sternum to the wrist where they're gripping the stick, the idea is after you've created lower body torque, you've produced speed through the core, you're now going to accelerate the extremities, the arms, to a maximum point and then hyper stiffen or super stiffen, brace, slowing or bracing everything from the core out and accelerating the stick to the release of the ball. So graphically, what this looks like when you plot it out using 3D motion analysis is you will see the arm segment accelerate rapidly to a very high speed, 1,000 degrees per second, immediately decelerating as a function of the core bracing, and the stick accelerate away from the arms to its peak speed right at the point of release of the ball. So when this is done effectively, you get an extremely efficient, extremely high output with respect to shot speed. Now, not just distal end speed in terms of the speed at which the stick is moving and the ball is accelerating out of the net, but the explosiveness, the quickness with which you can pull this trigger is dramatically improved when you can brace and accelerate the extremity. So to highlight what we've just talked about, a couple of years ago, we did some research where we looked at a group of elite-level college players. And we looked at the differences between players that could shoot and had shot speeds, or with a gun, ball speeds of 90 to 100 miles an hour versus those who were under 90. So we had a group of elite-level college players from elite-level programs, and we broke them into groups, equal groups that were shooting above 90 essentially and below 90. We essentially had groups of 6 above 90 and 5, so they're about equal groups. And then what we did was we compared the key parameters as we just discussed to see if there was any significant difference in the patterning or the movement between those shooting above 90 and those below 90. The first thing that we looked at was left knee extension or lead leg stabilization. It was the most significantly different, and as we discussed, because we worked from the ground up, had the greatest impact on the ability to shoot above 90 miles an hour. And we had guys in the group that were shooting just a little over 100, so we had like high 90s and 100, to like 102. So we had some significantly fast shot speeds. And the difference, as you can see, is the dark line is the higher level athlete, for the higher level shot. They came in at a 40 to 45 degree lead knee angle and stayed braced in that position throughout the entire acceleration phase. It wasn't until they got close to release that they extended the knee a little bit, and it was only minor. The other group, the group that shot below 90, came in with a much straighter leg, and as they came into foot contact, bent the knee significantly, and then extended significantly. So there's a lot of knee movement going on when we need that knee and that leg to be stable and translating ground reaction force into the lead hip or into the pelvic girdle. So the most significant difference between those shooting above 90 and those below 90 boiled down to lead leg stabilization to show you how important lead leg stabilization is to producing shot speed and explosiveness power. When you look at the deceleration of center mass, it wasn't as dramatic of a difference, but still a significant difference. What you saw was both athletes, both groups came in at about the same speed when they were shooting. However, because of the lead leg stabilization, the center of mass deceleration of the high-level shots, or the shots above 90, was significantly greater than the deceleration of those below 90. So the ability to stabilize the lead leg directly relates to their ability to control their center of mass and essentially produce pelvic speed, or control the center of mass to create torque, to produce rotational torque off of the linear momentum. So again, you can see how important lead leg stabilization is and the impacts of lead leg stabilization on shooting speed as well as explosiveness and power. Now, this graph I combined. When you talk about core bracing and snapping the whip, when you put them together, you're essentially talking about the kinetic link. And the kinetic link is essentially combining core differentiation with the bracing component. What you'll see here, and it's a little tough because this graph is pretty busy, but what you'll see is the dark lines are the shots above 90. You'll see that there was better sequencing as we discussed between the hips, the shoulders and the arms, and then release of the stick itself. With the dotted line, which is the shot below 90, what you see is a very limited differentiation. The lower body and the upper body and the arms to some degree all accelerate about at the same pace. They reach their peak speeds through the impact zone, and there's very little active bracing and very little acceleration of the stick. Most of the speed was generated by the upper body, the torso and the arms, kind of pulling the stick through rather than snapping or cracking the whip and accelerating the stick. So again, it's a little busy graph, but you can see the culmination of lead leg stabilization and control of center mass in both differentiation and bracing. Just real quick, this is sort of a scientific summary. Players that generated 90 mile an hour, above 90 mile an hour speed exhibited better ability to decelerate forward momentum. That's the control of the center mass. Those above 90 exhibited better ability to stabilize the lead plant leg and generate torque, as we just discussed. And players that generate above 90 mile an hour speed exhibited better ability to coordinate body segments and sequential pattern, transferring speed more effectively to the lacrosse stick. And that's our core differentiation and bracing, which we refer to as one group as the kinetic link. So the last thing I kind of want to just kind of finish up with in terms of application of this information. Now, what we typically do with these webinars, with this level of webinar, is just overview the basic parameters, overview the biomechanics aspect, and then do a basic overview of how we can integrate this information into training and coaching. As we move into the winter, we're going to do more involved case studies where we're actually going to look at specific athletes and data and talk about developing programs around their deficiencies and very specific protocols and progressions. But today, as more of an overview, what I want to talk about is how we can use this information to have significant impact on improving performance. At the same time, we're improving performance. We're improving performance through efficiency. Improved efficiency, we're going to limit the compensations that the athlete goes through to create shot speed, which is going to minimize or at least reduce the risk of mechanical injury. The more compensations we have, the higher stress we produce on smaller joints and smaller body segments, the more potential to create forces that will lend themselves to mechanical injury or overuse type injury. So what I want to talk about a little bit is just a quick overview of how we use PSP or progressive skills training to actually train key aspects of coordination. Now, I'm not going to get into a whole thing about what progressive skills training is. If this is new to you, if you haven't joined us before and you don't know what progressive skills training is, or if you've heard us talk a little bit about it, but you haven't really been able to view any of the webinars on PST, I would highly recommend that you go to our website or go to our YouTube channel, and there's at a minimum a PST primer, which is a short 30-minute webinar on what PST is. It's a really great webinar. I would suggest if you haven't watched it, go watch it. If you have, just as a refresher, go watch it. Progressive skills training, just as a quick overview, is not strength and conditioning. It's also not coaching techniques. Progressive skills training, a lot like the biomechanics, is meant to fill the gap between strength and conditioning and coaching and train coordination, neuromechanics, as opposed to just physical strength, mobility, or the technique of making a shot. There's lots of ways you can teach technique. There's lots of types of technique for any sport. Progressive skills training looks at the key biomechanical parameters and facilitates the coordination of those parameters, or the production of those movement patterns. So we're essentially looking at and impacting coordination and the ability to, for example, lead leg stabilize, core differentiate, and brace. Those are distinctive biomechanical parameters. You can be the strongest, most flexible kid in the gym and not be able to brace. You can also have the most beautiful looking technique out on the field and not be able to brace. So what we want to do is we want to look at those parameters as something that is going to augment the ability of the athlete, really to take their physical attributes and hone them into what they're learning as in terms of shot technique. So I'm just going to give you 2 examples of ways that we can be smart. We can take strength and conditioning principles and strength and conditioning type exercises, and we can take the biomechanical knowledge that we have in terms of what these patterns, what these key biomechanical parameters or patterns are, and we can teach the body to move more efficiently. So here's a really simple exercise that can be done in the gym that's probably being done in the gym with less impact than if we tweak it a little bit. So this is essentially just a basic med ball toss. This actually, the concept can be applied to all kinds of variations of med ball tosses, chops and lifts with a med ball, any kind of explosive chest passing or diagonal type movements. We do this with many, many variations. This is a very simple horizontal med ball toss into a wall. The key here is what we're doing with this exercise with the Swiss ball between the knees is we're putting the leg in a 40 to 45 degree angle. We're forcing the foot to be in solid contact with the ground, and we're forcing the knee to stay in a 40 to 45 degree angle while we produce torque and differentiate through the core by using a med ball, throwing med ball. So you can see what we do, and it seems simple, but it's incredibly effective because what you're doing is you're teaching the body to brace the lead leg appropriately while creating torque and differentiating through the core and accelerating the med ball into the wall. So it's a simple exercise, but what we look at it as, when you do it in the gym, typically in a strength conditioning program, you're just strengthening muscles. You're just you're strengthening muscles and producing speed or power. You're doing, basically like a plyometric or a power-based med ball exercise. When you stick the ball between your knees, you are now facilitating neuromechanical adaptation. It's a slight difference, but it's a massively impactful difference. What we do is we teach the athlete how to stabilize the lead leg, which we know from the data is absolutely critical to producing shot speed. And as a function of stabilizing the lead leg, we teach the body how to accelerate the lower body, differentiate through the core, which is absolutely critical, and do that in a stable lower body position. So we are getting all the benefits that we would from a standard med ball exercise, but we're facilitating neuromechanical adaptation, both lead leg stabilization as well as core differentiation. It's absolutely impactful. If you tweak these exercises, and this is what we do with PST, we do this, we've got many, many variations for many different scenarios. But what we do is we tweak basic exercise to be more impactful to the neuromechanics or the biomechanics of the movement. Here, let me give you one more before we wrap up and kind of summarize. Bracing. Bracing is something that has to be done at speed. It's not something that you can do in the gym on a cable or a cable machine, or and even with the med ball, you're talking, even if you're just using a 4 or 6 pound ball, it's heavy. The stick is not that heavy. So we have to be able to move at speed, and we have to teach the body how, when moving at speed, how to accelerate or snap or crack the whip. So what we do here is, again, this is a very simple type looking exercise. We use the ball again to keep facilitating lead leg stabilization, okay? So we're doing that. We are going to be engaging the same stuff we did in the previous exercise, so hence the word progressive skills training. We keep adding to the movement. We're emphasizing core differentiation. But now we are actually cracking a whip. In this case, what we use is a towel that has length properties and girth properties that are close to the lacrosse stick. And what we do is we fire the towel into an impact bag, or you could use a heavy bag, or there's different scenarios you could use. And then there's times where we work away from the impact bag at all and just have them snap through. And again, there are many variations of all kinds of things that we can do. We can use lacrosse stick with some weight to do dynamic chops and lifts and stuff. There's so many different things we can do. But this exercise is key, because what you're doing is, with a lacrosse stick, you can work the lacrosse stick through the release zone, the acceleration zone, with your arms. And many kids, and even older guys, even at a higher level, get away with that a little bit. But the elite level athlete is really snapping the stick, is really bracing and allowing the stick to fire away from the extremities and release with optimal speed. So what we do with this exercise is we use an implement that's not rigid like a stick, that can't be manipulated with the body, with the arms and the upper body. It has to be snapped. And if you don't brace, you cannot snap. And you do this at speed. Body segments are moving at speed, similar, identical really, to the lacrosse shot itself. You'd be surprised, as simple as this looks, the vast majority of your, especially younger kids who haven't developed the ability to brace at all, cannot snap the towel right away. And it's teaching them how to, super stiffening happens in literally milliseconds, in fractions of a second. You have to be able to brace, stiffen, and allow the implement to fire. And so teaching the kids through lower body stabilization, lead leg stability, core differentiation, and then snapping the towel forward through a brace action, teaches them how to do that. Once they've learned how to brace, when they fire a shot on the field with their lacrosse stick, they brace. They don't know that they're bracing. It happens too fast for them to be cognitively aware of or voluntarily kind of bracing, but they brace. Once you teach the body how to stiffen, you can stiffen. And then we just keep honing it with more and more types of exercises, and we go from there. But these are just some just a couple simple ways to show you how we can use the data that we collect on athletes in a generic way, obviously, to understand, but in an individual way. So from a ZenoLink perspective, when we look at an athlete, we do a 3D motion test, and we look at their ability to lead leg stabilize, core differentiate, and brace. We see what they do well, what they don't do well, what positions of the body are in, how well they stabilize, dynamic core posture, how well they accelerate the pelvis, what speeds they're attaining, things like that. And then we can customize programs based on where their deficits are. So we don't waste time doing things, teaching them things they already do well. We focus on their deficits and then mesh what their improvement in those areas of deficit with things they do well to create a better overall coordination. So, again, this is just a small overview of the types of things that we can do. I'm pretty much going to wrap up there, but I think there was maybe a question. There was a question about sort of like what's the proper form to achieve maximum speed. And from a technique perspective, again, we're not talking about technique. You know, there's lots of variations of technique and lots of different ways to teach technique. But from a movement perspective, maximum speed on a shot is a direct derivative of your ability to maintain a 40 to 45 degree angle at the lead knee through the acceleration phase of the shot, to stabilize the core so that you can move rotationally and differentiate, and then to brace as the shot is taking off, as the ball is being accelerated away from the stick, bracing to allow momentum to be transferred to the ball as efficiently as possible is what's going to produce maximum shot output. So, and the thing is, we've tested many elite level athletes, both collegiate and professional, and they all have different styles. They all have different body types. They all have different shot styles. They've all learned a little differently. They all come from different backgrounds. They all have strengths and weaknesses. Inside that, or underneath what you see as their technique, they all move essentially the same. In other words, they all lead leg stabilize incredibly well. They control their center of mass incredibly well. They differentiate and they brace and they accelerate their extremities incredibly well. So from our perspective, from the ZenoLink perspective, what we want to do is evaluate body movement, the neuromechanics or the activity-specific coordination, evaluate where an athlete does things well and where they don't do things well, evaluate what issues might be contributing to that. If they are weak or immobile, we have to address those things, obviously, and then teach them how to use their bodies more effectively to create shot speed or whatever the pattern might be. We do the same thing with acceleration, although we didn't talk about it tonight for with respect to lacrosse, with respect to shot, obviously. In lacrosse, acceleration and speed, just foot quickness and acceleration, the ability to get up to speed quickly, change direction, is obviously very important, just like it is in football and hockey and other sports. We look at that as well. We look at an athlete's ability to change direction or accelerate, not from a technique perspective, but from the ability to coordinate push and pull, pushing against the ground and then pulling off of the ground to facilitate acceleration forward. And then changing direction is a lot like what you see here is the control of the center of mass, the sort of the reverse of accelerating, the deceleration using stabilization at the joints and deceleration of the center of mass, and then, you know, change of direction the opposite way. Same thing goes for vertical jump or any other activity like that. And there's a few other quick questions, and I'll try to answer these, and then we'll kind of wrap up. Is the whip similar to lag in golf? Absolutely. I mean, it's different because obviously it's a different sport. You're gripping the stick differently than you grip the club, and or baseball bat. So there's obviously differences, but from a biomechanics parameter perspective, they are identical. They're analogous. So the whip that we're talking about is similar to the lag in a golf swing or the lag in a baseball swing. It's the same thing, just in the context of the lacrosse shot. Here's a question, are there videos of testing on the athletes? Will this webinar be able to be watched again? Yeah, we have a whole bunch of sample videos. If you're interested in seeing more information, just contact us. We've got sample videos of testing and of data and of PST protocols, and we love to share. And this video, as well as, or this webinar, as well as all of our general public webinars, can be found on our blog and on our YouTube channel. And I think it's YouTube/ZenoLink. If you don't know what it is, just go to our website, ZenoLink.com, and we have links to Facebook, Twitter, YouTube, and the blog. And everything is posted there, and you can download it, view it, whatever. What other exercises that train the body? What other exercises are that train the body in these aspects? There are a ton of different exercises that we can use. There are core, what we call specific PST exercises, which are developed around activity-specific functions. So we try to match activity coordination or activity-specific coordination with the exercise, and we always start slow, but our main focus is to produce the same speeds and the same conditions of the actual activity itself, only doing it in an exercise form. You know, we're working on plyometrics, or we're working on ballistic speed output or stabilization or something like that. In addition to those PST exercises, very specific, activity-specific PSTs, we also employ other types of functional training, not as strength conditioning specialists, but as ways to augment the neuromechanical reaction and neuromechanical facilitation. So we may take some specific PSTs, like I just showed you, like using the ball between the knees and snapping the towel into an impact bag, and we might, with that, use say for example a kettlebell or a dumbbell push press action, or even like a push jerk action, where the core is driving the extremity. Or we may do a dumbbell or a kettlebell snatch exercise prior to doing that to facilitate, sort of almost like a movement prep, to facilitate sort of that neuromechanical movement, and then go to the activity-specific exercise like snapping the towel. So there's a lot of variation. We're not going to get into tonight, but if you have questions, just contact us. Just email me. My email's in the invite and a follow-up on this, or just use contact at contact at ZenoLink.com. Contact us, and I'll sit down with you. I'll take you through stuff. And like I said, later in the winter, right now we're just overviewing a lot of different sports, and then when we get into the winter, we'll be focusing more on case studies and actual protocols and matching exercise and progressions with the biomechanical data. ZenoLink is based on biomechanical data, so when we work with athletes, and we typically work with athletes through coaches and through strength conditioning specialists, not directly, although we have in the past worked occasionally with athletes, we typically work through partners who are the coaches and the strength conditioning specialists or the therapists. When we work with these athletes through those partners, we start with a biomechanical assessment, and that starts with a 3D motion capture, which we do out on the field or the clinic using 6-stop DLT motion data that actually runs off the standard video collection, so you can just be out on the field. I mean, there's some categories, do a little calibration, do some specific things for us, but basically take your video cameras out to your field, do the calibration, and collect data on your athletes right out on the field and their equipment. And then we can take a look at how well they perform these activities. It can also be done, obviously, indoors or even in a clinic in a controlled environment. But so we start with that 3D, and then we go from there. So we're going to be talking about, we're going to look at specific case studies with data and match specific protocols to that down the road. But if you've got questions now, just email us or call us, and we'll sit down with you and take you through it, show you a bunch of examples, and share what we've got with you. So I appreciate everyone attending tonight's webinar, and look forward to having you guys at future webinars. We'll be having a couple next week, and I think a few after that. So we're going to be doing kind of doubling up and having a couple of weeks here for a while as we get more into the fall. So hopefully we'll see you at a future webinar. Thanks a lot for attending.